Hello, geometry students. Today we're going to be covering the Unit 8 workbook. So we're going to be covering everything in the Unit 8 packet. Okay, so go ahead and get that packet out, and we'll start working on that right away. All right, I'm going to share my screen with you, and let's take a look. So you can go ahead and open your packet and we'll go straight to page 6. And we're going to talk a little bit about what a tangent is. Okay, so a tangent is usually, well, in the context we're talking about here, it's when you have a circle and then you have a line that touches it at exactly one point. So that's called a tangent line. Now, it's not just for circles, right? Like you could have a curve or something, and you could have a tangent line to that, where the tangent line just touches the curve at one point. So that is considered a tangent line. So here's an example of not a tangent line. You see how the line goes through it twice? So that would not be a tangent line. Now, one of the main things with circles is that when you have a tangent line to a circle, and then you have a radius that touches that tangent line, then that forms a right angle. So that's kind of what they're demonstrating here. So if you have a tangent line and then you have a radius from that circle, then that forms a right angle. So these would be perpendicular. The tangent line and that radius would be perpendicular to each other, meaning forming a right angle. Okay, so let's talk about what the implications of that are. So if you have two tangent lines, so let's say from M, you have two tangent lines. You have ML and MN. So that tells you that these are both right angles. These are both 90 degrees. Now from there, we can figure out the measure of angle X, because within any four-sided shape, the total measure of all the angles should equal 360. So if I know that this is 90 and this is 105 and this is 90, then I can find X, right? So the shortcut basically is that I could just do 180 minus the 105. In other words, this interior angle here formed by these tangents or whatever, and the radius, and this X are supplementary, meaning they add up to 180. So that tells you right away that this is 75 degrees. So X is 75 degrees. I repeat that again. This angle here and this angle here will add up to 180 degrees. They are supplementary, we would say. Okay. So with that, this must be 60 degrees, right? Because these two angles should add up to 180. And indeed it is. That's great. Now for a tangent line, you could also think about the example here for this quick check is talking about, like, oh, what if you have an observation tower, right? So you have an observation tower sitting on a planet, and the distance that you can see to the horizon is tangent to the planet itself. So we're going to talk a little bit about what this means for us, like how far you'd be able to see to the horizon. But we should be able to at least pick out some things here. So one thing I want to emphasize is that this triangle is a right triangle, right? Because you have the radius here and you have the tangent. Well, remember, the radius and the tangent form a right angle, right? We just discussed that. So this triangle is actually a right triangle with E at the right angle. And then C is at the center of the circle, and T is at the top of that observation tower. Right? So from T to E, that's the distance you'd be able to see. From E to C, that's the radius of the circle, right? The radius of the planet in this case. So in this one's problem, EC, that distance there is 1,450 kilometers. And then what would be the distance of CT? Well, hopefully you can see that CT would be the radius plus the length of the tower. So the radius plus the length of the tower is only 0.3 kilometers. So the radius of the planet plus the height of the tower is 1,450.3 kilometers. Okay. So what is the length of CT? That's this, right? So 1,450.3 kilometers. What is the length of EC? Well, that's just the radius of the planet. That's 1,450 kilometers. What is the measure of angle E? That's talking about this. We already talked about that's a 90-degree angle. It's a right angle, in other words. Let's do some problems that have to do with this. So like I showed you with this example, these two angles should be supplementary to each other, meaning they add up to 180. So for this one, the measure of X here, well, you can see it, the answer kind of got cut off there, but if you just do 180 minus the 122, that should give you a 58-degree angle for X here. With that being said, see if you can do number 1 and number 2 on your own. Again, these two angles should add up to 180. These two angles should add up to 180. Once you're done with that, let's move on to this page right here, page 9, and we'll talk about how to do this problem here. So it says a tower has an observation deck about 1.2 kilometers above ground level. So you can see the height of the tower in this case is 1.2 kilometers. About how far is it from the observation deck to the horizontal, knowing the planet's radius is 2,900 kilometers? So we're looking from the top of the observation deck to point E, right? So we want to know what's that viewing distance there. Well, since we know that the viewing, right, is tangent to the circle, that tells us that this is a right angle right here. So at angle E there, that's a right angle. So I'm going to go ahead and draw this triangle to the side. And we know it's a right triangle because angle E is a right angle. Here's where E sits. T is at the top of the tower. We'll put it here. And then C is at the center of the planet. Now we know the radius of the planet. So the radius of the planet, in other words, from C to E is 2,900 kilometers. Now what's the distance from C to T? Well, that would be the radius of the planet plus 1.2 kilometers more. So the radius of the planet, 2,900, plus 1.2 kilometers more. So that would be 2,901.2 kilometers. And we want to know what's the viewing distance, right? So what's the distance here? E to T. So that's what I want to know. What's the distance from T to E? Now, when we have a right triangle and we're missing one side length of a right triangle, how do we find that missing side length? Well, hopefully you remember that would be, we can use the Pythagorean theorem here, right? A squared plus B squared equals C squared. Now, which of these are A, B, and C, right? Where in other words, where does my X go? Is X one of A or B, or is X the C? Well, the C is always the longest side. The C is always the hypotenuse, right? Now, in our case, the longest side of this right triangle, the hypotenuse, is TC, right? It's opposite from the 90. You can see that there. The 90 always points to the hypotenuse, the longest side. So our A and B in this case are 2,900 and X. It doesn't matter which one's A, which one's B. I'll just put X first. So the two legs of this right triangle are your A and B. And the C is the hypotenuse. In other words, the longest side. And that also gets squared. So now with our calculator, we're going to do, so we have X squared plus, and then we'll do 2,900 squared. So this is a large number. It's 8, 4, 1, and 4 zeros. 1, 2, 3, 4. Use your calculator and make sure you get that same number and you know how to find that. Okay, so that would be 2900 squared. That means 2900 times 2900. Then do the same with the c squared. So that's 2901.2 squared. So that would give me 8, 4, 1, 6, 9, 6, 1.44. Now I want to get x squared by itself. I want to get x by itself. So what we're going to do next is subtract the 841,0,0,0 to both sides of this equation. That'll leave me with just x squared on the left side. And on the right side, when you subtract these, that'll leave you with 6961.44. Now, hopefully you remember from units in the past that in order to get rid of the squared, in order to get rid of this squared here, what you're going to do is square root both sides of this equation. So in order to get rid of squared, you square root. That'll give us x by itself with these square and square root canceling. Over here, if I do the square root, so on my calculator, I want to do the square root of 6961.44. Now on my calculator, and maybe on yours as well, I have to press the second key first. I have to press the second key and then press x squared, and that gives me the square root. Okay, so make sure you know how to find the square root on your calculator. Right? Different calculators might be a little bit different, but you should get the answer 83.4. 83.4. That's fine. And since it's all in kilometers, we would say that that's 83.4 kilometers. Okay. Make sure you're able to get that on your own on your calculator. Now the Pythagorean theorem is not going to go away. We're going to see it again in these problems here. In this one, we have a tangent line. AB is tangent to this circle, okay, circle C. So AB is a tangent, and X is the radius here. So notice I've got this right triangle. And what length is the hypotenuse? Is the hypotenuse AB, or is it BC, or is it CA? Well, remember, the 90-degree angle always points to the hypotenuse. Okay, the 90-degree angle always points to what's going to be the C in our Pythagorean theorem. Okay, so we're finding a missing side length on a right triangle. So we're going to use the Pythagorean theorem. A squared plus B squared equals C squared. So again, this is for finding a missing side length on a right triangle. You use this formula. Now in this case, our A and B, those are the two legs. Right? In our case, that's 13 and X. So I'll put the X first, but it doesn't really matter. You can put 13 first. Doesn't matter which of those is A and which of those is B, but it does matter that C is the hypotenuse. In our case, the hypotenuse is this. It's CA. So what is that distance? What is the distance from C to A? Well, it's X plus 7, isn't it? See how this total distance is X plus 7 more. So this distance, CA, is X plus 7, and that's going to get squared. Right? The C, the longest side, the hypotenuse, gets squared there. So this left side, let's just say this is X squared plus, now what's 13 squared? Well, remember, that's 13 times 13. So that's 169. And then on the right side, well, we need to square this out. So x plus 7 squared, well, that means x plus 7 times x plus 7. So on the side here, maybe as a side work, I'm going to put it over here. x plus 7 squared, I want to do that. So x plus 7 squared is the same as saying x plus 7 times itself. So x plus 7 times x plus 7. Now, I don't know if you remember from algebra, but in order to multiply these two binomials together, what you're going to do is you're going to do what we call foiling, or you may have heard it called foiling. Basically, it's this first term, the x, multiplies with both of the terms from the other one. So the x times the x, then the x times the 7. From there, you'll multiply the 7 times both of these. So 7 times x, and then 7 times 7. So both of these terms multiply with both of these terms when you multiply these two binomials together. So x times x, well, that's x squared, x times x. Then x times 7, put plus 7x. So that's x times 7 is 7x. Then 7 times x is another 7x. So we're multiplying the 7 times x, that's 7x. Then 7 times 7, so that's 49. Lastly, we want to combine like terms if there are any. So in this case, the 7x and the other 7x, these are like terms. So we can combine those together. In this case, this would be x squared, does not combine with these other x's, plus 7x plus 7x is 14x, plus 49. That looks like a T. Plus 49. Okay. So when we do x plus 7 squared, that gives us this right here. So that's x squared plus 14x plus 49. Okay. Now you may notice there's an x squared on both sides of the equation. So what we can do is go ahead and subtract x squared on both sides. So I'm going to subtract x squared and subtract x squared. And what that does for me is it cancels this x squared on both sides. That's good. It makes my equation much simpler. My next step, so now I only have 169 over here on the left. On the right, I have 14x plus 49. Now I still want to get x by itself, so my next step would be subtract 49 both sides. Hopefully you're following along and write everything that I write, you should be writing. Okay. So over here on the left now, 169 minus 49, that's 120. And then on this side, 14x. So it's over here. Lastly, to get x by itself, we divide both sides by 14. Divide both sides by 14. So that cancels that. You're left with x on this side. And on this side, we could just do it as a decimal, 120 divided by 14. That gives me, we'll say 8.6 if I'm rounding to the nearest tenth. So 8.6. So now, what did that tell me? So that's my answer, right? But what did that tell me as far as this picture? Well, that tells me the radius of this circle, right? Because x is the radius of this circle. So 8.6 is the radius there. Okay. Now, I'm going to help you set up for this question here, question 5, but I'm going to expect you to do most of the work on your own. So I'll help you with the setup, though. So we have this right triangle, and we want to set up the Pythagorean theorem, right? A squared plus b squared equals c squared. So think, which side length would be the c? In other words, the hypotenuse. Well, the 90-degree angle always points towards the hypotenuse. So in our case, the hypotenuse is AC once again. The hypotenuse is AC once again. So our A and our B are the other two side lengths, the 22 and the x. So x squared plus 22 squared, those are the legs of the right triangle, equals the hypotenuse squared. So in our case, that's x plus 14 squared, okay? See if you can finish it from there, okay? Just try to follow the steps that we did from the last problem, and also you have an example up here as well. Now, for the questions on page 11, it's asking, is ML a tangent to circle N at point L? So they're asking, is ML, is this a tangent line to the circle? Well, remember, there's a way we can tell if it's a tangent line. If it's a tangent line, then this will make a right angle. So if it's a tangent line, this will form a right angle. So, but we don't know if it will or not. We need to figure that out. So if it's a tangent line, this will form a right angle, which would make this a right triangle. So basically all we have to do is check, is this a right triangle? So the way we can check if it's a right triangle is, once again, by using the Pythagorean theorem. So if the Pythagorean theorem holds true, if this ends up being correct, then we know this is a right triangle. Therefore, we know this is a right angle. Well, which length should be my C? Well, the C is always the longest side, the hypotenuse. In our case, if this is a right angle, we don't know if it's a right angle or not, but we know that this should be the C because it's always the longest side. And let's check. So our C in this case is 10. And we don't know if it's equal yet, so I'll put a little question mark over the equal sign. But we want to, well, I'll put a question mark over the next equal sign. This one, question mark. Because I don't know if it's equal yet, okay? But then this is our A and our B, the 6 and the 8. So 6 squared plus 8 squared. So let's work this out. Let's see if it's equal. If it is equal, then this is a right triangle. Okay, so 6 squared, that means 6 times 6, that's 36. 8 squared, that's 64. And is this equal to 10 squared? Well, 10 squared is 100. So is this equal? I don't know. 36 plus 64, well, that is 100, isn't it? So this over here is 100, and that definitely does equal 100. I don't need to put a question mark because I know that's equal. So then therefore I could say, yes, ML is tangent to circle N. Okay, yes, ML is tangent because this ended up being equal. Therefore, we know this is a right angle because we know this is a right triangle. So if this is equal, we know it's a right triangle, which means we know this is a right angle, which means ML is definitely tangent. Because remember, if it hits at a tangent, then that forms a right angle. Now I want you to go ahead and try number 7. If it ends up being equal, then yes, ML is a tangent. If it's not equal, then we'd say no, ML is not a tangent. So go ahead and give that a try. Once you're done with that, let's move on to section 8.2, or 8-2, I should say. Now these definitions, you can go ahead and read them on your own and try to make sense of them from the picture. But I'll explain them as we go, so just give them a read, see if they make sense from the picture, and then we will, same with these. But let's go and let's talk about these right here. So these are just from the definitions. So we're not going to spend too much time discussing them, but I'll show you, I'll say what should go here. Okay, I'll just tell you what should go there, and you can write it in on your own because it's going to take too long for me to write it. So this one says, if a diameter bisects a chord, so you have a diameter, that means a line going across the middle of a circle, bisects a chord. So bisects means it cuts it into 2 equal parts. So cut it into 2 equal parts here. And then over here, we would say, then the chord and the diameter are perpendicular. And you can see that forms a right angle, perpendicular. So I'll tell you again. Then the chord and the diameter are perpendicular. Go ahead and write that in there. If a diameter bisects a chord, then the chord and the diameter are perpendicular. Okay. Number 2. If a circle has 2 congruent chords, so you can see these 2 chords are the same length. They're congruent. That's what these called tick marks here. Those are to indicate that those are congruent. So whenever you see those little tick marks, they're telling you that this is congruent to that. So if you have 2 congruent chords, then the arcs are also congruent. So we'd write, then the arcs are also congruent. Then the arcs, these are the arcs. Then the arcs are also congruent. So these arcs will be the same length. Number 3, if a circle has 2 congruent central angles, so see these little swooshes on these angles, that means they're trying to tell you that those 2 angles are congruent. So if you have 2 congruent central angles, then their chords will also be congruent. Then their chords will also be congruent. And you can see that here, this chord and this chord. See how they have those tick marks? That means those chords are also congruent. Okay. So go ahead and fill those in. Once you're done with that, let's move on to page 15. And for the most part, we're going to work on these, but I think for the most part, if you kind of just look at the picture and try to make the most logical guess and what they're trying to tell you, usually these aren't too bad. So the first thing I want to point out is you got this circle here. There's a lot of numbers. There's a lot of letters. There's a lot going on here. But the one thing I do want to point out is you see how these little have this PQ and QR, they have those tick marks. That means that those are the same length. So PQ and QR are the same length. So we know that QR must be 11, right? Because they have those little tick marks. They're telling you those are congruent. So what's the length of PR? So what's the length of PR then? Well, you can see the length of PR is from P to R, that's 22, isn't it? Right? The length from P to R is 22. So what do you suppose the length from R to S is? So what do you think the length from R to S would be? Well, I hope you could see that it'd be the same length as from P to R. It would be the same as from S to R, right? Because these are both 8. You see that? So these chords are the same. So that would also be 22. You can kind of see that PR and SR are the same length. Here, what is the value of x to the nearest tenth? Well, x is talking about the distance here from the center to this chord here. What is that length there? Well, it should actually be the same as this length here. So the length of x is the same as the length over here. So that means x equals 6.7. Okay. I hope you can see why that is so. Okay. Each of these questions are a little bit different from each other, so we'll just kind of go over all of them. Looking on page 16, what I want to point out is this triangle right here. So we got this triangle right here. And what kind of triangle is that? What kind of triangle is that? Well, hopefully you can see that if this is a right angle right here. See that little box? That means that it's a right angle also on the inside of this triangle. So that means this is a right angle over here as well. So what we've got is a right triangle. So this triangle here is a right triangle. I'm going to draw it a little bit bigger over here so we can clearly see what's going on with the right angle right here. Now this length here is x. That's what we want to find. Now what's the length of this part right here? This part of the triangle? Well, all the way across is 18. You see that? All the way across this chord is 18. So from here to here would only be half that. That's 9. Right? Half of that 18. What would be the length of this part of the triangle? This would be the hypotenuse. What would be the length of the hypotenuse of this triangle? Well, it should be half of the diameter. You see that? Half of this 26. Well, that makes it 13. So now we know two sides of this right triangle, and we're missing a third side of this right triangle. Well, how do we find a missing side length on a right triangle? The Pythagorean theorem. In this case, the hypotenuse, the C, is 13. So our A and B are x and 9 in this case. So when we use the Pythagorean theorem, a squared plus b squared equals c squared, our C in this case, the hypotenuse, is 13. The other two side lengths are the 9 and the x. So our legs are length 9 and x, while the hypotenuse is length 13. So this would be x squared plus 9 squared, that's 81, equals 13 squared, that's 169. Subtract 81 from both sides of the equation in order to get x squared by itself. So that'll give me x squared over here on the left. And on the right, we get 88. Lastly, to get rid of the squared, use square root both sides. So that'll give me just x by itself because squared and square root cancel. The square root of 88 gives me, we'll say 9.4. So make sure on your calculator you get that. Mine says 9.38, but I would round that 3 up to a 4 because it's an 8, right? 9.38, they rounds up to a 4, up the 3 to a 4. Okay. With that, let's go ahead and try number 7 here. I'll help you set it up, but I expect you to do the finishing of it. Okay. First thing I'm going to do is I'm going to draw this triangle a little bit bigger over here so we can see what's going on. And hopefully you can see that this is a right triangle, isn't it? A right triangle. With this length, NK is 7. The length KL is X. And what's the length from L to N? Well, hopefully they're trying to show you that 18 is the length of this entire chord. So if this chord is 18, then what would be the length here? Well, that would be half of it. So that'd be 9. In this one's case, which of these sides would be the hypotenuse? Would it be the 7, the x, or the 9? Well, hopefully you can see that the 90-degree angle, the right angle, is pointing towards the x. That tells you that the x is the hypotenuse. So our A and our B are 9 and 7. So this would be 9 squared plus 7 squared equals the hypotenuse squared, x squared. This gives us 81 plus 49 equals x squared. 81 plus 49, 130 equals x squared. We're going to square root both sides in order to get x by itself. That gives me 11.4. So that means the length of this is 11.4. Oh, shoot. I told you I was going to make you do that on your own. Oh, well. Yeah, the length of the hypotenuse, 11.4. I hope that those made sense. Now let's talk about, let's go on to 8-3, and we're going to talk about inscribed angles. So an inscribed angle, I basically just want you to know that an inscribed angle has its vertex on the edge of the circle, okay? So the answer key says these are all inscribed angles, right? Because all of them have the vertex on the inside of that circle. But this one's not an inscribed angle because its vertex is outside that, right? See how its vertex is not touching the circle? Now the proper definition, with the proper definition, I think only this one is an inscribed angle because only this one has the chords ending on the circle there. See how this one continues past, this one continues past the circle, right here and right here. See that? Same over here. So this is the only one that I would say is definitely definition of an inscribed angle. These other two are also in the answer key, so I would just circle all three, but just know that this is really the proper definition of an inscribed angle. The angle on the inside and the two chords like that. Okay. Now, I'm not going to talk about this too much because I want you to go ahead and read it, see if you can make sense of it, but I don't want you to worry if it's not clear right away or it doesn't really make sense, because we're going to be going over examples and I'm just going to explain it as we go. So go ahead and give those a read on page 18. Give all these definitions a read, see if they make sense to you. If not, don't worry about it too much because we're going to go over it in just a sec. Okay. For this one, you can fill these out by reading carefully. Like it says here, read carefully through pages 780 through 783 in the textbook, and you should be able to find the answers to all of these. But I'll just go ahead and give you what these answers should be. So, inscribed angle theorem, the measure of an inscribed angle is half the measure of its intercepted arc. So this should be inscribed angle, goes right here. What that basically means is that if you have an inscribed angle, so let's say this angle here is an inscribed angle, the measure of this angle will be half the measure of this arc. So if this angle is 20 degrees, then the arc would be 40 degrees. Yeah. Corollary number 1, two inscribed angles that form, you want form right here, the same arc are congruent. So if you have two inscribed angles forming the same arc, so let's say you have this inscribed angle here, and then you have this arc that's formed, and then you have another angle that forms that same arc, then these two angles will be congruent. Okay, form. Theorem 12-12, the measure of an angle formed by a tangent and a chord, so here you want chord, is half the measure of the intercepted arc. For this next one, number 4, corollary 3, it looks like they didn't space these words out very well, but it should say the opposite angles of a quadrilateral inscribed in a circle are supplementary. So if you have a quadrilateral, that means a four-sided shape that's inscribed in a circle like this, that means like this angle and this angle, the opposite angles, will be supplementary. So those will add up to 180. Same thing with like these two angles would be supplementary to each other. Okay, so are supplementary, supplementary. Corollary 2, an angle inscribed in a semicircle is a right angle. So what that's saying is if you have a circle and you have a semicircle, so that's like cut in half, and then you have an inscribed angle that hits that, well, then this is a 90-degree angle. So that means this would be a 90-degree angle. My picture's not the best, but there you go. And again, in this case, the hypotenuse here is the semicircle, or the diameter, which creates a semicircle. These will all make sense as we go over some examples, but right here it should be semicircle. Okay, let's move on to page 20. Now these will start to make sense as we go through these, but basically with these two problems, the main thing you want to really get out of it is that whatever angle is here, whatever angle is an inscribed angle, then the arc that's formed is twice as much. Okay, so if I just look at this part right here, so our angle RQS, You see that? Angle RQS. See how it's forming the arc from R to S? So RQS is forming this arc from R to S. You see that? So ignore the rest of these lines in the picture, but just look at RQS, and that's forming this arc. So what I want you to really learn is that whatever this angle is, this arc will be twice that measure in degrees. So that means A in this case is double what that is. So in this case, A is 160 degrees because this is 80 degrees and this will be twice as much. Okay. Now it goes back the other way too, right? Like if I knew that this is 160, but I don't know the angle, well, I could take 160, cut it in half, and get the angle. Okay. So if I know the arc, I can find the angle. If I know the angle, I can find the arc. All right. So with that in mind, let's go ahead and see if we can find the measure of angle B. So here we're trying to find this measure here, angle B. So now I would look at the angle that forms that. So that's RWT. See how angle B is RWT? Ignore this rest of the stuff. Now, I don't know what that angle is, but I do know the arc. The arc goes from R all the way to T. You see that? From R to T. See how the angle RWT is forming this arc, R to T? So what is this arc? What is the measure of this arc from R to T? Well, I know A is 160. I know A is 160, and I know from S to T is 34. So from R to T would be 160 plus 34. So from R to T is 194. So the arc from R to T, this arc, I put a little arc over it, is 194 degrees. Do you see that? I'm adding from R to S and then from S to T to get from R to T. So if I know that this angle, or this arc I should say, is 194, then what would be the measure of this inscribed angle? Well, that'd be half of that. So that means B will be half of this. 194 divided by 2. That gives me that B must be 97 degrees. Okay, 97. Now I know A and B. There you go. I know that perhaps was a little bit tricky, but we can go on to number 7 here. I'll go ahead and work this one with you. So here they give you, I'm going to go over this one a little bit faster, but they give you angle RQS is 67. So what would be this arc from R to S? Well, it would be double whatever this inscribed angle is. So this arc, A, will be double the measure of this. So 67 times 2 gives me that A is 134. Okay. Now I want to find this angle here, R to W to T, this angle here, B. So in order to find B, I want to know what is the arc from R to T. So the arc from R to T, this arc, is from R to S, which is 134, plus from S to T, which is 42. So this arc from R to T is, add those together, right? So that'd be 176. To find this inscribed angle measure, it would be half of that. So 176 divided by 2 gives me that B is 88 degrees. Not squared, degrees. Again, because this arc from R to T is 176, so the inscribed angle will be half of that. Okay. Now we're using the other formulas that we talked about. For this one, this inscribed angle, angle 1, is kind of making a semicircle here. So this arc, one way to think about it is this arc is 180 because it's a semicircle, right? So this arc is 180 degrees. So what would be the measure of the inscribed angle? Well, it's half of that, right? So if I know the arc, I know the inscribed angle is half of that. So that means that angle 1 would equal, or sorry, I'll put the M angle 1, so the measure of angle 1 equals 90 degrees. It's half of that, which makes sense because we learned from one of the formulas earlier was that whatever this arc is, then this will be half of that. Half of 180 is 90, and there you go. For this one, number 9, they have that this angle right here is 35 degrees, and this angle covers the arc from this point to this point, right? You see how this angle, this inscribed angle, forms this arc? Well, this inscribed angle, angle 1, also forms that same arc, right? See how angle 1 forms that same arc? Well, if two angles form the same arc, well, then that means that those two are congruent. Now, it should make sense because this 35-degree angle would produce an arc of 70 degrees, right? Because it's double it, right? And since this is 70 and this forms the same arc, it should be half as much. So that's 35, right? So the measure of angle 1 is 35. Basically, if those two share the same arc, then they must be congruent because they're both inscribed angles. For this one, we learned that if you have a quadrilateral inscribed in a circle, then the opposite angles should be supplementary, meaning they will add up to 180. So that means that the measure of angle 1, M angle 1, for the measure of angle 1, is, well, 110 degrees. Because again, these two angles should be supplementary to each other. Okay, that's it. Let's go on to problem 11 and 12 on page 22. So in the diagram, SR is tangent to circle Q, or tangent to the circle at Q. If the measure of arc PMQ is 134, what is the measure of angle PQR? So we're looking for the measure of the angle PQR. So PQR, that's what we're looking for. We want to know what that angle is. Well, they tell us that the arc PMQ is 134. So PMQ is 134 degrees. But we want to find this angle right here, PQR. So one way to look at this is, well, since I know that this is 134, this arc, I can figure out this angle here, right? This angle right here. Because if the arc is this, the angle is half of that, right? The angle would be half of that. So 134 divided by 2, that's 67. So this would be a 67-degree angle on this side. So what would be the measure of the angle on this side? Well, these two angles, they form a straight line. Remember, you may not remember this, but in some units ago, we talked about on a straight line, if you have two angles that form a straight line, let's say like this. So if one of them is 67, then these two angles should form 180 degrees. They're supplementary because they form a straight line. Those are called a linear pair. I don't know if you remember that or not, but these two angles form a straight line, and a straight line is always 180. So if I do 180 minus that 67, I'll get the measure of this other angle, which is 113 degrees. Okay. Let's take a look at number 12. In the diagram, SR is tangent to the circle at Q. If PMQ is 121, find what PQR is. So here in PMQ, this arc is 121 degrees. And we want to know what's the measure of this angle here. Okay. See if you can figure out what that is from here. Again, this one was 113 was our answer. Okay. See if you can figure out this one by following this one's example. You can always rewind the video and watch that one again. See until it makes sense. Once you're done with that, let's move on to 8-4. Okay. Let's just, you can look at these, theorems here, but don't worry about too much. We'll cover those in detail. Should make sense when we do them. Okay. Same over here. You could look at these, but again, we're going to go over them in more detail. So in this one here, you could say that A times B will equal C times D. Just following this one here. Okay. So when you have two intersecting lines like that, then these lengths multiplied will be these lengths multiplied. And you have these other formulas here for these various scenarios. And we're going to go over some examples that kind of talk about those. Okay. But first off, we're going to talk about these two here. So in this case, you have an angle. So there's two intersecting chords, and you have an angle at that intersection. In order to find that angle that's there, what you're going to do is you find the average of these two arcs. So the average of this arc and this arc. So how do I find the average of two things? Well, you'd add them up, divide by 2. Okay. So that's how you find average in general, is you add up all the items and divide by how many there are. But if I'm just trying to find the average of 2 items, I would just add up those 2 items and divide by 2. So I'm finding the average between 84.2 and 50.6. So 84.2 plus 50.6. You add those up and divide by 2. That'll give you the average, which will tell me that angle measure. 84.2 plus 50.6, 134.8. And then I'm going to divide by 2. That gives me 67.4 is the measure of x. Okay. That tells you the measure of this angle and the measure of this angle. Those will always be the same. Those are actually vertical angles, if you remember that. With that example, see if you can find the answer for question 2 here on page 25. So pause the video and go ahead and do that. Next page. Here's a lot of words and a big example, but I'm going to show you how to not do it this way. Let's take a look at the question, what it's asking. It says a satellite is in geostationary orbit above Earth's equator, has a viewing angle of Earth formed by the 2 tangents to the equator. The viewing angle is 38.9 degrees. So the viewing angle of the satellite is right here. So that's 38.9 degrees. Okay. What is the measure of the arc of Earth that is viewed from the satellite? So it's talking about the arc that goes from here, this arc here. So from A to B. They want to know how many degrees is that arc. Well, you can follow this example if you like, but there's a shortcut, and I'll just show you the shortcut. What you need to know is like the measure of this arc and the measure of this angle are actually supplementary to each other, meaning they add up to 180. So if I just do 180 minus that measure here, that the satellite's viewing angle, then that should give me the measure of that of that arc. So 180 minus 38.9 gives me that the viewing arc is 141.1 degrees. Okay, so 141.1 degrees. With that being said, see if you can do number 4 on your own. Okay, so go and pause the video and do that. Once you're done with that, let's move on to page 27. So here they give you one example here, and this example is pretty good. Essentially, we're going to be using this formula here. And you can see there's lots of letters. There's a W, X, and another W. There's a Y, a Z, and another Y. But if you look at where each of the variables are, it'll make a lot more sense. So like if you look at where X is, though that's where the 12 is here, right? So everywhere you see an X in the formula, in this case, there's just one X, that's where you'd put 12. So we're just going to use this formula here and replace each variable with where it goes. So for example, X, well, that's 12 here. So I'm going to put 12 where the X is in the formula. Okay. There's a plus sign here. Okay. Now W is right here. Okay, so where's W in my picture? Well, W is where 9 is, right? So 9 is what my W is. So I'm going to put, everywhere you see a W, I'm going to put a 9. So that means there's a 9 here for this W, and there's a 9 out here for this W. Then look at where Y is. So Y is right here. Where's Y here? Oh, that's right here. So I'm going to put, everywhere you see a Y, I'm going to put 8, because that's where 8 corresponds to where the Y is there. So I'm going to put 8 for Y in those two spots there, where there are Y's in the equation. Lastly, Z, well, Z with Z, okay, so that's Z right here. Now my goal is to figure out what is Z. I want to find the value of Z in this case. So over here, let's go ahead and figure out what this left side of the equation equals. So the first thing I would do is add the two things in the parentheses, 9 plus 12, which is 21, and then multiply by 9. So 189. Over here, maybe I'll distribute this 8, right? You could distribute this 8 here. The reason I have to distribute and I can't combine these, well, I can't combine the 8 and the Z. You see that? So I can't really add these two in parentheses. So I can distribute this 8, though. So that's going to be 64 plus 8Z. I like to put a little cross in my Z's so I don't mix them up with 2's. Anyway, so now we want to solve for Z. So I'm going to go ahead and subtract 64 both sides of the equation. So on the left side, that gives me 125. And on the right side, these cancel, so that leaves me with 8Z over here. Lastly, to get Z by itself, we're going to divide both sides by 8. So that'll give me Z equals 125 divided by 8, 15.625. Or we can just call it 15.6 is fine. Okay. So now that you've seen that example, go ahead and try number 6 on your own. All right, it's the same deal, just different numbers. Now we're going to talk about circles. Here's the general equation for a circle. You got to kind of have this one memorized. But the idea is that H and K is the center of the circle. So the center of the circle will be some coordinate point. Maybe in this example down here, the center was 8 and -2, 8 comma -2. So that tells you your H and K right there. The H is 8 and the k is -2. The h is 8, and the k is -2. So then you'd plug those into the equation here. R is the radius of the circle. So hopefully you know what the radius means, but it's from the center to the outside of the circle, okay, to the edge of the circle. Okay. So in the quick check, what does h and k represent in the standard equation for a circle below? H and k is the center of the circle. Okay. So h comma k tells you the center of the circle. This will make sense as we do some examples here. So, and you can, if they give you an equation of a circle like this, you can graph it, because if you have the equation, you should be able to find h and k. So that tells you the center of the circle, and you should be able to find the radius. So the radius in this case is going to be 3, because remember, in the standard form of equation, this has r squared, right? R squared. So in this case, if r squared is 9, well, to find r, you would square root both sides, and that'll give you that r is 3. Okay. And your h and k, well, in your standard form equation, it has x minus h and then y minus k, right? So in this case, your h would be -3. So your h is -3, and your k is 2. Okay. No, it's kind of opposites in what you'd think, right? But if it says x plus something, remember in the standard form of the equation was x minus h. So that's x minus -3. That's what makes the plus. Okay. Again, it'll make more sense as we go over some examples. Let's go ahead and write the standard form equation of a circle that has center at -5, -2, and a radius of 25. So here's our standard form of equation. And whatever I write, you should be writing. So you should just be following along, writing everything that I'm writing. So I'm just going to rewrite this standard form equation. Every equation that I don't have memorized, I definitely want to write the formula or the equation at the beginning of the problem. That way I know exactly which formula I'm using, okay? At least until I have it memorized. In this case, my h is -5. That's from your center, right? And your k is -2. So your h and k are right here. And your r, your radius, is 25. So now we're just going to plug in h, k, and r into the equation. So it'll be x minus, and what's my h? Oh, h is -5. So that's x minus -5. And then that thing gets squared. So x minus -5 squared plus y minus, what's my k? -2. Okay. And then that gets squared, right? Equals the radius squared. So my radius is 25. And that gets squared. See, this will become x minus 5. You see that? That becomes x plus 5. So hopefully you remember from, adding and subtracting positive negatives, that when you have a minus negative, that makes it a plus, right? Hopefully you remember that. Plus, then over here, y plus 2 squared equals, and then you just do the 25 squared here, which I think is 625. Yeah, 625. Okay, and there you go. With that example, see if you can do number 2 on your own. So again, find your h, k, and r, plug it into your standard form for a circle equation, and then go from there. Once you're done with that, let's go on to page 31. So here we want to graph a circle, and they give us the equation, okay? X minus 2 squared plus y plus 1 squared equals 9. Well, we know from our standard form of a circle equation, it's x minus h squared plus y minus k squared equals r squared. So in this one's case, x minus h, x minus 2 it says, right? So that means my h is 2. So my h is 2. Can you guess what the k is in this case? This would be negative 1, right? See how it says y plus 1? Well, that would mean k is negative 1, because y minus negative 1 is what makes the y plus 1 there. So that tells you the center of your circle, and it's kind of hard to see the axes here, but the y-axis is right here, and the x-axis is right here. But my center of my circle is at 2, negative 1. So I'm going to go ahead and put a point, 2, negative 1. That's the center of my circle. That's the center of my circle. And the radius, well, notice 9 is over here, and that's where r squared lives. So 9 is r squared. So how do I find my radius? Well, to get the squared to get the r by itself, you need to get rid of the squared. So you're going to square root both sides. That'll give me that r equals the square root of 9, which is 3. So that tells me I have a radius of 3. So from my center, I know I'm going to have a radius of 3. So what I'll do is I'll go 3 to the right. From the center, go 3 up. From the center, go 3 to the left. And from the center, go 3 down. And then now I've got 4 points that are part of the circle, and I could just kind of connect them with a smooth curve. My picture's not the best, but hopefully yours looks a little bit better than that. But that creates your circle there. Just kind of try to connect those points with a smooth curve. Don't try to just go straight there, because then that forms like a diamond or a square, right? We don't want that. We want a curve, right? We want to make a circle. Okay. Let's see if we can do the next one here. So in this one, what's my h and what's my k? So remember, it's x minus h. So that means my h is negative 2. Because remember, it's x minus h. So that's x minus negative 2 to make the plus 2. And my k is 3. So I know the center of my circle should be at negative 2, 3. So negative 2, 1, 2, 3. Again, this is my y-axis, and this is my x-axis. And I go 2, negative 2, positive 3, like that. Now, my standard equation has r squared over here. So my r squared is 4 in this case. So how do I get r by itself? Well, you square root both sides. That'll give me that the radius is square root of 4, which is 2. So I have a radius of 2. So I'm going to go from the center of my circle, I'm going to go 2 up, 2 to the right, 2 down, and 2 to the left. Again, from the center. Connect these with a smooth curve. Okay, that one's a little bit better, to make a circle. Now we're going to talk about what's called a locus of points. So a locus of points is just a description of points. Okay, so in this case, it says a locus of points is all the points that satisfy a certain condition. So they'll give you some condition or some rule you have to follow, and then you draw all the points that follow that rule, and then you create some sort of shape. Okay. Here, the example they give you is what are all the points that are 2 centimeters from a point C. So if you have a point C, and I want every point that is 2 centimeters away from it. So I would go 2 centimeters in every direction from C. So this distance is 2 centimeters. This distance is also 2 centimeters. This distance is also 2 centimeters. This distance is also 2 centimeters. See how I can create a bunch of points that are 2 centimeters away from C in every direction? Now, these aren't all the points. I can create I can keep on creating points that are 2 centimeters away, right? But if I continue to make points forever that are 2 centimeters away, I would eventually make, hopefully you can see, a circle, right? With a radius of 2 centimeters. So the locus of points that fit this description, what are all the points that are 2 centimeters from some other point, C? That would form a circle with a radius of 2 centimeters. Here's another example they give. Make a sketch of the locus points that are 1 centimeter from AB. So here you have AB, and I want every point that is 1 centimeter away. And you can see them starting to make some points that are 1 centimeter away in every direction. Eventually, you'd get this shape right here, where this distance or this distance or this distance, each of these distances are 1 centimeter away from this segment AB. Okay, so you'd create this sort of ellipse-like shape. Not quite an ellipse, but whatever. Here, another example, make a sketch of locus of points that are equidistant, meaning the same distance, from the endpoints A and B. So here are A and B. I want every point that is the same distance between them. So here's a point. The distance to A is the same as the distance to B. So that would be in the locus. So with this one, because the same distance to A or same distance to B. Here's another point that's the same distance to A or B. Here's another point that's the same distance to A and B. You can see I can continue to make these points that are the same distance to A or B, and eventually you would make this right here, which you describe as a perpendicular bisector of AB. So that's what you would eventually produce. Okay, hopefully you can see that there. Okay. So those are some examples of what they're talking about when they mean a locus of points. You're just drawing every point that fits that description. Then eventually you'll create something and you'll just describe it. So let's try number 1 here. What is a sketch and description for each locus of points in a plane? The points are 1 inch from a given point C. So I've got a given point C, and then my locus of points is every point that is 1 inch away. So I want to go 1 inch to the right, maybe. From C, I want to go 1 inch to the left, 1 inch up, 1 inch down, and 1 inch in every direction, right? So 1 inch over here in this direction, over here, 1 inch from C, 1 inch from C. This isn't perfect, but hopefully you can see that I'm forming each of these. Let's just pretend they're all the same distance from C. And then you would get eventually a circle with radius 1 inch. 1 inch. So then the description that you would say is the locus of points forms a circle with center at point C and radius 1 inch. I'll repeat that. The locus of points will form a circle with center at point C and radius 1 inch. Number 2 is a little bit trickier. What is a sketch and description for each locus of points in the plane? Okay, the points are in the interior of angle ABC. So first, hopefully you have a straight edge, but if not, well, just do your best to make a straight edge here. That's pretty good, actually. Pretty good. So I'm making an angle ABC. So let's say A, B, C. And I want all the points that are on the interior, so they have to be in the inside of this angle here, and they are equidistant from each of the rays of angle ABC. So these are considered the rays. So AB is a ray, and BC is also a ray. And I'm looking for all the points that are the same distance to these rays, and they need to be in the interior. So this point does not work, for example. Yes, it's on the interior, but it's not equidistant to these rays, right? See how it's closer to this ray than it is to this ray? So this would not be in the locus of points. This point I just made is not in the locus of points. Here would be a point that is in the locus of points. Okay, see how it's on the interior, right? It's on the interior of the angle, but it's also the same distance to each of the rays. Like the distance to this ray is the same as the distance to this ray. So this would be an example that is, this point is in the locus of points. All right. Hopefully you can see that this one is too, right? See how it's on the interior and the distance to each of the rays is equal. Here, here, here. So hopefully you can see I'm forming another ray that goes through the middle of this angle. Okay, so this is the picture of this locus of points. Now what's the description? I'll go ahead and tell you. What we just formed is an angle bisector. So we just split angle ABC. We split it into two congruent angles. So what we've created is an angle bisector. So what we'd say is the locus of points forms an angle bisector for angle ABC. The locus of points forms an angle bisector for angle ABC. Okay, and that's it. Next is the review. So go ahead and give the review a try. Answer all the ones that you can, and just do your best. I will make another video that covers all the questions in the review, but just do all the ones that you can, and I'm sure that you'll be able to get most of them done. Well, with that, that's the end of the workbook. I hope that wasn't too bad. I feel like this unit in particular covers a lot of different things, but none of them are that bad. And I hope that I was able to help you make sense of it. Well, with that, I will see you next time. Have a great day.